June 6th, 1944, 17:30 hours, aboard HMS Dispatch, English Channel. Admiral William Tennant grips the rail as his vessel navigates through the largest invasion fleet ever assembled. Behind him, stretching to the horizon, hundreds of vessels begin their strange procession. Not warships charging into battle, not troop transports disgorging soldiers. These are concrete caissons, each the size of a 3-story building, each weighing 6,000 tons, being towed at 4 knots across 100 miles of open water. Tennant had commanded the evacuation of Dunkirk 4 years earlier, improvising piers from abandoned trucks driven into the surf to save 338,000 men. Now he watches an audacity that makes Dunkirk look modest. The Allies are bringing 2 complete harbours to France, each the size of Dover, the prefabricated sections for 600,000 tons of concrete and steel infrastructure floating behind tugboats like a procession of industrial icebergs. The Germans control every port from Norway to Spain. Hitler has spent 2 years and 13 million cubic meters of concrete fortifying them. The Allies' response eliminates the requirement for ports entirely. They will land supplies faster than Germany can manufacture them, using facilities that did not exist 48 hours ago. What Tennant cannot know as he watches this engineering armada cross the Channel is that in 13 days, the worst storm in 40 years will strike these artificial harbours. One will be destroyed completely. The other will survive by margins measured in feet of wave height. Yet even in failure, the Mulberries will prove a truth about industrial warfare that the Germans discovered too late. Modern war is won not by capturing enemy infrastructure, but by manufacturing your own faster than the enemy can destroy it. The mathematics of the Mulberry Harbors reveal an Allied industrial capacity so overwhelming that German intelligence officers who studied the invasion would conclude the war was already lost before the first soldier stepped onto French soil. The disaster at Dieppe had demonstrated with brutal clarity what every Allied planner feared. On August 19, 1942, 6,000 troops, mostly Canadian, assaulted the French port of Dieppe in a raid intended to test German coastal defences and gather intelligence. The attack collapsed within hours. Of 5,000 Canadians who landed, 3,367 became casualties. 30 Churchill tanks bogged down in the shingle beaches, unable to move. German defences around the port operated exactly as designed. Concrete bunkers with interlocking fields of fire turned the harbour into a killing zone. Naval gunfire could not suppress the fortifications. Aerial bombardment proved ineffective against reinforced concrete. The tanks that reached shore could not negotiate the seawall or overcome obstacles. The lesson emerged with mathematical precision. Every major port on the French coast had been transformed into a fortress. The Germans had concentrated their strongest defences where logic demanded harbours must be captured. Cherbourg bristled with coastal batteries and fortified positions. Le Havre housed massive gun emplacements. Calais anchored the heaviest concentrations of the Atlantic Wall. An assault on any defended port would require weeks of siege warfare, while the invasion force consumed supplies faster than they could be landed over open beaches. Vice Admiral John Hughes Hallett, naval commander for the Dieppe raid, voiced the conclusion that would transform the invasion plan. "If a port cannot be captured," he stated in the after-action conference, "then one should be taken across the Channel." The concept seemed absurd. Ports require deep water, sheltered anchorages, piers, cranes, warehouses, road networks built over decades. How could such infrastructure be transported across 100 miles of the English Channel, the most unpredictable waters in the world, with tides reaching 23 feet and storms that could generate waves exceeding 20 feet? Winston Churchill had actually sketched the basic concept in 1915 during his time as First Lord of the Admiralty, proposing artificial harbours off German islands. The memo had been filed and forgotten. In May 1942, frustrated by the slow progress on solving the port problem, Churchill issued a characteristically direct memorandum titled Piers for Use on Beaches. The entire text demanded immediate action while acknowledging the engineering challenges. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. That brief memo initiated one of the most ambitious engineering projects of the war. The specifications bordered on fantasy. 2 complete artificial harbours, each capable of handling 12,000 tons of cargo daily, equivalent to Dover Harbour's peacetime capacity. Construction to be completed in less than 2 years. Every component prefabricated in Britain, towed across the Channel and assembled in less than 2 weeks. The structures must withstand 23-foot tides, survive Channel storms, and operate for at least 90 days. They must accommodate Liberty ships drawing 28 feet of water alongside smaller landing craft. The piers must allow continuous offloading regardless of tide conditions. All of this to be accomplished while maintaining absolute secrecy, as the Germans must not discover the invasion would occur on open beaches rather than at captured ports. The Quebec Conference of August 1943 authorised full-scale production. A committee of Britain's leading civil engineers, Colin R. White, J.D.C. Cooper, J.A. Cochrane, R.D. Gwither, and Lieutenant Colonel Ivor Bell designed the final specifications. The solution they devised consisted of 3 integrated systems, each representing innovations in marine engineering. First, breakwaters to create sheltered water. Second, pierheads that could rise and fall with tides. Third, floating roadways connecting the piers to shore. The British gave each component a colourful code name as part of operational security. The entire project became Operation Mulberry, the name chosen at random from the next available code word in the secret code volume. Sir Bruce White, one of Britain's leading consulting engineers, had discovered a document labelled Artificial Harbours on his desk without proper classification markings. Appalled at the security breach, he demanded an immediate codename, leading to the adoption of Mulberry. The breakwater system combined 3 distinct elements, each using different principles to absorb wave energy. Gooseberries consisted of obsolete ships deliberately sailed to the invasion beaches and scuttled in predetermined positions. 74 vessels, ranging from worn-out merchant ships to retired warships, would be sunk to create lines of breakwaters off all 5 landing beaches. The ships provided immediate protection, but could not stop the largest waves. Behind them would be positioned the Phoenix Caissons, massive concrete structures that formed the primary breakwater. The Phoenixes dwarfed anything previously attempted in temporary harbour construction. The largest type measured 200 feet long, 60 feet wide, and 60 feet high. These giants displaced 6,044 tons when empty. Smaller versions ranged down to caissons, displacing 1,672 tons. In total, 213 Phoenix caissons would be constructed in 6 different sizes. The engineering challenge of building these structures revealed the desperation and brilliance of British wartime engineering. The caissons required 330,000 cubic yards of concrete, 31,000 tons of steel reinforcement, and 1.5 million yards of steel shuttering. No prototypes could be built given the compressed timeline. Instead, scale models were tested at the National Physical Laboratory in Teddington for towing characteristics, sinking procedures, and wave action effects. The models validated the designs without alteration, a remarkable achievement given the unprecedented nature of the structures. Construction began at 14 sites around the British coast before the designs were even finalised. 24 leading civil engineering firms, including companies still operating today such as Balfour Beatty, Costain, Henry Boot, Sir Robert McAlpine and Taylor Woodrow, undertook the work under contracts managed by a special Ministry of Supply department directed by Sir John W. Gibson, who received his knighthood for the achievement. The construction sites transformed London's bombed docklands into emergency shipyards. Graving docks at Middlesbrough, Goole, Southampton, and Tilbury became concrete foundries. Several units rose in an entrance lock at Plymouth and in the city's floating dock. 2 London docks, the East India and South Dock, were dewatered after engineers constructed precast concrete dams in the entrance locks. 18 caissons took shape on the dock bottoms, with hundreds of thousands of cubic yards of blitz rubble used to create construction beds. 23 units were built on slipways constructed on the foreshore at Stokes Bay, Stone Point, and Langston Harbors, near Portsmouth. Workers laboured around the clock. The caisson construction represented the largest concrete pouring operation in British history. Each structure had to be watertight, structurally sound enough to survive towing, and precisely engineered to sink in controlled fashion once positioned. The hollow chambers inside would be flooded to settle them on the seabed, creating an artificial reef that would dissipate wave energy. Some Phoenix caissons that sank prematurely during construction or towing still rest on the British coast today. Visible at low tide at Thorpe Bay in Southend-on-Sea, at Pagham in West Sussex, and in Portland Harbour in Dorset. The third element of the breakwater system consisted of bombardons, large floating structures fabricated from steel and rubberized canvas. These cross-shaped units measured 200 feet long and 25 feet wide, anchored outside the main breakwaters of Gooseberries and Phoenixes. 24 bombardon units attached to one another with hemp ropes would create breakwaters extending 1 mile. The bombardons were designed to absorb wave energy through their floating motion, reducing the force that reached the inner harbour. The Royal Navy took responsibility for the bombardon design, while the Royal Engineers managed all other Mulberry components. This division of labour would prove consequential when the Great Storm struck. The pierhead system represented perhaps the most innovative aspect of the Mulberry design. The final design came from Lieutenant Colonel William T. Everill and Major Alan Beckett of the War Office's Transportation 5 Department, who devised floating pontoons linked to pierheads with integral spud legs. These steel pontoons rested on massive legs that could be raised or lowered with hydraulic jacks to maintain constant height above sea level regardless of tide conditions. Each pierhead required over 1,000 tons of steel. The prototype, completed in the Solway Firth by April 1943, underwent months of testing in conditions similar to Normandy's tidal regime. The testing ground near Garliston in Wigtownshire offered the necessary combination of large tidal range, sandy and rocky seabed, and heavy gales, all while remaining isolated enough to maintain operational security. The pontoons measured approximately 200 feet long and 60 feet wide. 4 steel legs or spuds descended from each pontoon. When driven hard against the seabed by hydraulic pressure, the pontoons rose to maintain their position. This allowed the pierheads to accommodate the 23-foot tidal range off Normandy while keeping their decks at constant elevation. Alternatively, the pontoons could float with the tide, sliding up and down the legs. Ships could moor alongside the pierheads and offload cargo directly onto the deck, regardless of tide state. The pierheads included quarters for personnel, technical rooms, storage spaces, and facilities for rapid unloading of large landing craft. Some piers featured sloped metal surfaces that ran gradually into the sea, creating artificial beaches where landing ship tanks could open their bow doors and drive vehicles directly onto the pier under their own power. After successful testing, approval went to approximately 200 firms throughout Britain for large-scale manufacture of piers and pierheads. The majority of construction took place at Leith, where waste ground transformed into erection berths. Other major sites operated at Conway in North Wales under Messrs Joseph, Parks and Son, and at Military Port No. 1 at Cairnryan, where the Army handled all erection work. Connecting the pierheads to shore required floating roadways that could twist with waves while supporting the heaviest military vehicles. The system, codenamed Wales, consisted of 80-foot bridge spans supported on floats. Each span used 2 80-foot girders carrying a 10-foot wide roadway, with the complete unit weighing approximately 30 tons. The engineering achievement lay in flexibility combined with strength. The roadways could twist vertically until one end reached 40 degrees to the other, while still carrying the heaviest equipment at speeds of 25 miles per hour. The panels were loosely bolted to cross members, allowing articulation without failure. The roadways rested on pontoons of steel plate or reinforced concrete, codenamed beetles. The concrete beetles used precast panels 1.5 inches thick, joined by concrete ribs cast in place. Steel beetles provided the same function with lighter weight. Road sections 500 feet long could be towed as single units, consisting of 6 spans including 5 bridge sections, and the shore ramp float. Approximately 10 miles of floating roadways would connect the pierheads to shore across both Mulberry Harbors. Construction contracts for the whales went out in June 1943 through normal Ministry of Supply channels under the Director General of Mechanical Equipment. The fabrication required approximately 50,000 tons of steelwork for the piers and roadways combined. This massive steel requirement competed with shipbuilding, aircraft production, and tank manufacturing for limited resources. The prioritization of Mulberry components demonstrated the project's strategic importance. Every ton of steel diverted to harbour construction represented 1 less tank, 1 fewer aircraft, 1 postponed merchant ship. The British accepted this trade-off because the Mulberries made the invasion possible. Without artificial harbours, the logistical calculus of the landing became impossible. The army calculated that 12,000 tons daily would be required to sustain the invasion force once breakout from the beaches occurred. Open beach operations could handle perhaps 4,000 tons under ideal conditions. The gap of 8,000 tons daily meant the invasion would stall within weeks, as units exhausted ammunition, fuel, food, and replacement equipment. The secrecy surrounding Mulberry construction tested British security procedures to their limits. Thousands of workers across more than 200 firms knew they were building strange concrete structures and peculiar steel bridges. None knew the ultimate purpose. The Ministry of Supply issued cover stories for each construction site. Workers heard they were building anti-submarine barriers, offshore oil storage facilities, even components for breakwaters in Dover Harbour. The massive concrete caissons being built in London's docks supposedly would protect the Thames estuary from renewed bombing. The floating piers under construction in Scotland allegedly supported a facility for testing new landing craft. The compartmentalization of knowledge extended to the companies themselves. Firms building phoenixes had no contact with those constructing whales or beetles. Assembly sites remained separate from construction locations. Only a handful of senior engineers and military officers understood how the pieces would fit together. The scale of the deception extended beyond the construction sites. British intelligence conducted an elaborate campaign to convince German spies that the invasion preparations targeted Calais. The massive activity in southern England, including Mulberry staging areas, was explained through false information suggesting the preparations supported the attack on Pas-de-Calais. Wooden and inflatable tanks created dummy army camps. Radio traffic simulated the presence of massive formations under General Patton's fictitious 1st United States Army Group. The Germans observed genuine construction activity, but interpreted it through the lens of their assumptions about where the invasion must occur. The Mulberries, perhaps the clearest indicator of the true invasion plan, went undetected because German intelligence could not conceive that the Allies would attempt landings without capturing a port. One security breach nearly compromised the entire operation. In May 1944, the Daily Telegraph crossword puzzle published several code words related to D-Day, including Mulberry and the names of all 5 landing beaches. MI 5 Secret Service officers interrogated the compiler, Headmaster Leonard Dorr. Investigation revealed that Dorr routinely asked students for word suggestions. Many of these students lived near US military barracks and had overheard soldiers using the code words without understanding their significance. MI5 concluded the appearance was coincidental, but maintained surveillance on Dorr through the invasion. The incident demonstrated the challenges of maintaining operational security for a project involving hundreds of thousands of workers across 2 years of preparation. By early June 1944, the Mulberry components had been assembled at staging points along Britain's south coast. Over 400 towed component parts weighing approximately 1.5 million tons waited for the invasion order. The logistics of the cross-channel movement rivaled the invasion itself. Each Phoenix caisson required a tug, sometimes several tugs for the largest structures. The block ships destined to become gooseberries would sail under their own power or be towed. The Whales, Beetles, Bombardons, and other components each had specific towing requirements and schedules. The movement had to be coordinated, so components arrived in proper sequence for assembly. Pierheads were useless without roadways. Roadways could not be installed until breakwaters provided shelter. The entire harbour had to become operational on a fixed timeline, regardless of weather or enemy action. Naval planners worked out towing schedules to the minute, calculating speed, distance, sea conditions, and potential delays. The afternoon of June 6, 1944, as Allied soldiers fought to expand their beachheads, the Mulberry convoy began its journey. 74 block ships destined for the gooseberries departed first, steaming or being towed toward the 5 invasion beaches. These vessels, many of them obsolete merchantmen or retired warships, carried crews who would sail them to precise coordinates, open seacocks, and abandon ship as they settled onto the seabed. The Phoenix caissons followed, towed by tugs at the glacial pace of 4.3 knots. The slow speed reflected the towing challenge. Each caisson presented enormous resistance, and tugs had to balance speed against fuel consumption and the structural integrity of towing cables. The journey of 100 miles required roughly 24 hours under ideal conditions. Any storm or equipment failure could add days or result in loss of the structure. British tugboat crews had practiced towing procedures for months, but the actual operation dwarfed the exercises. Royal Navy destroyers and corvettes escorted the convoy, protecting the vulnerable structures from potential E-boat attacks or submarine infiltration. German naval forces, decimated by years of attrition and pinned in port by Allied air superiority, could not seriously threaten the crossing, but the risk remained. On June 7th, D-Day +1, German reconnaissance aircraft photographed the Normandy coast and returned with images that senior officers initially dismissed as impossible. The Allies were constructing harbours from nothing in open sea. General Heinz Guderian later wrote in his memoirs about studying captured American supply documents and equipment. He concluded Germany faced an enemy with unlimited industrial resources, and that victory had become mathematically impossible. The artificial Mulberry Harbors represented industrial capability on a scale that challenged German comprehension. Each harbour was roughly the size of Dover Harbour, Britain's major port, but built specifically for this invasion and considered expendable. The psychological impact on German defenders watching this construction emerge offshore exceeded the physical effect of naval gunfire. They witnessed the complete invalidation of their strategic assumptions. At Arromanches, off Gold Beach, the first Phoenix caisson sank into position at dawn on June 8th, D-Day +2. Royal Engineers directed the operation from survey vessels, using precise coordinates determined from soundings taken on D-Day itself. The process of sinking a Phoenix required careful control. Valves opened to flood the internal chambers, and the massive structure slowly settled onto the seabed. The largest caissons descended through 30 feet of water, their positions marked by buoys for the following units. By June 15th, 115 caissons had been sunk to create a 5-mile-long arc from Tracy-sur-Mer in the west to Asnelles in the east. This became Mulberry B, designated for British and Canadian forces. The caissons rose approximately 30 feet above sea level at low tide and 10 feet at high tide, creating a substantial barrier against wave action. Behind this breakwater, ships found protected anchorage, where offloading could proceed regardless of weather conditions outside the artificial harbour. Off Omaha Beach, the American Mulberry A took shape with similar precision but faster schedule. The US Navy Civil Engineer Corps directed construction, assembling prefabricated components under fire from German artillery that still held positions overlooking the beach. The block ships of the Gooseberries sank into position first, creating immediate sheltered water for landing craft. Phoenix Caissons followed, towed into position by tugs that maneuvered carefully in waters still containing obstacles and mines. German defenders, stunned by the scale of the invasion, watched helplessly as Allied engineering created harbour facilities before their eyes. By June 16th, Mulberry A became operational, 3 days ahead of the original schedule. Ships began mooring alongside the completed pierheads, their cranes swinging cargo onto waiting trucks that drove down the Whale roadways to shore. The American engineers had achieved remarkable efficiency, assembling a major port facility in 10 days. The achievement seemed to validate every assumption about American industrial might and organizational capacity. Then disaster approached from the northwest. On June 18th, meteorologists detected a weather system forming over the Atlantic that would develop into the worst channel storm in 40 years. Winds, reaching force 6 to 7 on the Beaufort scale, drove waves to heights exceeding 20 feet. For 3 days, June 19th through June 22nd, the storm battered the Normandy coast with conditions that exceeded the Mulberry's design parameters. The artificial harbours had been engineered to survive typical summer conditions in the Channel, where storms of this severity occurred once every 40 years on average. The Allies suffered catastrophically bad luck experiencing such conditions just 13 days after D-Day. The storm surge and wave action tested every aspect of the harbour designs. The bombardons, those floating breakwaters anchored outside the main caissons, took the first impact. Some sank as waves overwhelmed them. Others broke loose from their hemp rope moorings, possibly causing more damage to the harbours than the storm itself as they crashed into the Phoenix Caissons and Whale roadways. The breakwater system that should have protected the inner harbours partially failed, allowing massive waves to reach the piers and roadways. At Omaha Beach, Mulberry A disintegrated. The American harbour had not been as securely anchored to the seabed as the British installation. Recent research using modern wave hindcasting techniques has revealed that Omaha Beach experienced significantly larger waves than Arromanches during the storm, though both locations faced waves larger than design specifications. The combination of exposure, anchoring techniques, and wave height proved catastrophic. 20 of the 30 Phoenix caissons broke loose from their positions on the seabed. The floating Whale roadways, already stressed by continuous use, twisted and broke as waves lifted them far beyond their flexibility limits. The pierheads, pounded by seas from multiple directions, suffered structural damage that rendered them unusable. By June 22nd, when the storm finally abated, Mulberry A had been reduced to tangled wreckage. The harbour that represented months of planning, thousands of tons of material, and millions of man-hours of construction had been destroyed in 72 hours by forces of nature that exceeded all calculations. Salvageable components, including several intact Phoenix caissons, were simply towed to Arromanches to reinforce the British harbour. Where tens of thousands of men had streamed ashore across floating causeways, only coastal wreckage remained. The American response to this disaster demonstrated pragmatic flexibility that validated pre-invasion contingency planning. Without artificial harbour facilities, US forces reverted to beach operations, using techniques refined since the North Africa landings. Landing ship tanks drove directly onto the beaches at high tide, grounded themselves, opened bow doors, and disgorged vehicles and cargo. As the tide receded, trucks could drive alongside for loading. When the tide returned, the LSTs refloated and departed. This method required excellent weather and calm seas, but surprisingly achieved discharge rates that rivaled or exceeded the artificial harbour. Admiral John Leslie Hall had opposed the Mulberry concept from the start, arguing that LSTS over open beaches provided more flexibility. His prediction proved partially correct. American forces on Omaha Beach would ultimately achieve supply rates of 7,000 to 9,000 tons daily using beach operations alone. The calm seas created by the surviving Gooseberry breakwaters made this far more effective than expected, as the block ships continued to provide sheltered water even after the Phoenix caissons and piers had been destroyed. At Arromanches, Mulberry B survived the storm by narrow margins. The British harbour benefited from more sheltered position, better anchoring techniques, and operational decisions made during the storm itself. As waves threatened to overwhelm the structures, Royal Engineers pumped sand into some Phoenix caissons to increase their weight and stability. The additional mass prevented them from breaking loose, even as water surged around and through the concrete structures. Components salvaged from Mulberry A were integrated into repairs, extending the harbour and replacing damaged sections. Within days of the storm's end, Mulberry B resumed operations. The harbour would function continuously through November 1944, operating for 8 months instead of the planned 90 days. The British installation, now known as Port Winston after Prime Minister Churchill, ultimately landed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. These statistics represent more material than was used to sustain the entire Wehrmacht on the Eastern Front during equivalent periods. The British Mulberry alone handled supply volumes that exceeded the combined capacity of all French ports the Germans still controlled. The destruction of Mulberry A sparked controversy that continued through the war and into historical analysis. Critics argued the entire project wasted resources that could have been better employed building more LSTs or capturing French ports faster. The counter-argument emphasized that the Mulberries, even with one destroyed, provided psychological impact and insurance against contingencies. German morale shattered when defenders watched the Allies construct Dover-sized harbours from nothing within days. The demonstration of industrial capability convinced many German officers that resistance was futile, as the forces arrayed against them could manufacture infrastructure faster than it could be destroyed. Albert Speer, Hitler's armaments minister, provided the most eloquent testimony to the Mulberry's psychological effect. After the war, he stated, "To construct our defences in 2 years, we used 13 million cubic tons of concrete and 1.5 million tons of steel. A fortnight after the landings by the enemy, this costly effort was brought to naught by an idea of simple genius." The engineering lessons from the Mulberries influenced military and civilian construction for decades after the war. The wave action data collected during the storm contributed to improved understanding of extreme weather effects on marine structures. The failure modes observed at Omaha Beach led to better anchoring systems for temporary offshore installations. The floating pier technology developed for the whales found applications in Vietnam War logistics, where US forces built temporary piers on bare beaches. The concrete caisson concept influenced offshore oil exploration, where similar structures anchor drilling platforms in the Gulf of Mexico. The US military would later reference Mulberry designs when building a supply pier at Thule, Greenland, demonstrating that the underlying engineering principles remained valid for extreme conditions. In 2024, the US military announced plans to implement a modern floating dock for humanitarian aid in Gaza, using steel segments and concepts directly descended from the Mulberry whales. The specific technical achievements of the Mulberry project deserve recognition for pushing engineering boundaries. The Phoenix caissons represented the largest prefabricated concrete structures ever transported over such distances. The towing operation, moving 600,000 tons of concrete across 100 miles of open ocean, exceeded any previous marine engineering feat. The whale roadways solved the fundamental problem of maintaining connection between fixed and floating structures in tidal environments, a challenge that had limited harbour design for centuries. The spud pierheads provided the first large-scale application of jacking systems to maintain constant elevation regardless of tide state. Each of these innovations emerged from necessity, developed in months rather than years because the invasion schedule permitted no delays. The compressed development timeline forced designers to skip conventional prototype testing and commit to full-scale production based on mathematical modeling and scale model tests. This approach, risky in the extreme, succeeded largely through the quality of British engineering talent and the willingness to accept calculated risks. The human element of the Mulberry project reveals the forgotten contributors who made the harbours possible. The 45,000 workers across 200 firms who built the components often laboured without knowing their work's purpose. Welders joining steel sections for Whale roadways in Scotland thought they were building anti-submarine barriers. Concrete pourers in London's docks believed their caissons would protect the Thames from renewed bombing. Engineers who solved unprecedented technical problems received no recognition until long after the war. The tugboat crews who towed the structures across the channel, navigating in darkness to avoid submarine detection, faced dangers as real as combat, but received little acknowledgement. The Royal Engineers who assembled the harbours under German artillery fire, working 20-hour days to meet impossible deadlines, remain largely anonymous in historical accounts. Reginald D. Gwither, who directed the Corps of Royal Engineers operations and received appointment as Commander of the Order of the British Empire for his efforts, represents thousands, whose contributions enabled the project's success. The post-war fate of Mulberry remnants illustrates both the temporary nature of the installations and their enduring physical presence. Mulberry B, Port Winston, was decommissioned in November 1944 when Allied forces captured and reopened the port of Antwerp. The massive German fortress had surrendered after determined siege, and the deep-water port facilities, though heavily damaged, could be repaired faster than maintaining the artificial harbour. The Mulberry structures were simply abandoned in place. Concrete caissons that had cost hundreds of thousands of pounds to build were left to deteriorate in the surf. The steel pierheads and roadways, valuable for scrap metal, were partially salvaged, but much remained. Today, massive concrete phoenix caissons still line the beach at Arromanches, visible at all tide states, their purpose immediately apparent to anyone who understands their history. French authorities preserved several as historical monuments. The structures have become artificial reefs colonized by marine life, serving ecological functions their designers never imagined. One whale span from Mulberry B found unexpected preservation. After the war, it was reused as a bridge at Pont-Farcy in France. In 2008, a group called Les Amis du Pont Bailly, consisting of English and French volunteers, saved it from destruction. They gifted it to the Imperial War Museum, and it returned to England in July 2015. After conservation work, it became part of the Land Warfare exhibition at Imperial War Museum, Duxford, the only complete whale section preserved in a museum setting. 4 phoenix caissons that never reached Normandy found different purpose. They were later installed in the Netherlands, where they now house the Watersnood Museum or Flood Museum, serving as monuments to both Mulberry and the 1953 Dutch flood disaster. The repurposing of Mulberry components for civilian use fulfilled an unintended legacy, as temporary military structures became permanent fixtures serving peacetime functions. The mathematical reality of the Mulberry Harbors reveals the true scale of Allied industrial advantage. The 600,000 tons of concrete and steel used for the 2 harbours represented material equivalent to building 4,800 Sherman tanks or 15,000 trucks. The British diverted this material from conventional military production because the strategic calculation favoured the investment. The harbours would enable landing supplies at rates that made the material sacrifice profitable within weeks. The projection proved accurate at Mulberry B, which exceeded its planned throughput of 7,000 tons daily, achieving peaks of 9,000 tons. Over 8 months of operation, Port Winston landed 4 million tons of supplies. This figure represents more tonnage than passed through all German-controlled French ports combined during the same period. The comparison illustrates the fundamental asymmetry of Allied versus Axis logistics. Germany fought to preserve infrastructure built over decades. The Allies manufactured equivalent capacity in months and considered it expendable. The intelligence failure, represented by German inability to detect or comprehend the Mulberry preparations, compounded the disaster German commanders faced on June 6. German reconnaissance had photographed British coastal areas throughout 1943 and 1944, capturing images of Phoenix caissons under construction and whale components being assembled. Intelligence analysts filed these images as evidence of port expansion and anti-submarine measures. The conceptual limitation that prevented Germans from imagining artificial harbours derived from their own industrial reality. Germany could not have attempted such a project. The concrete requirements alone exceeded available production capacity. The steel needs competed directly with U-boat construction and tank manufacturing. The specialized vessels required for towing did not exist in German ports. Therefore, German intelligence officers concluded the Allies could not attempt it either. This failure of imagination, combined with the success of Operation Fortitude's deception plan, meant German commanders expected the invasion at Calais until weeks after D-Day proved otherwise. The Mulberries forced fundamental revision of German strategic assumptions about Allied capabilities. Field Marshal Erwin Rommel, commanding Army Group B responsible for defending the French coast, had repeatedly warned that the Allies possessed industrial resources that made defensive warfare futile unless Germany achieved quick victory at the waterline. After personally observing the artificial harbours, Rommel wrote to his wife that Germany faced enemies who had transformed war into an industrial process, where production statistics mattered more than tactical brilliance. His participation in the July 20th, 1944, plot against Hitler stemmed partly from this recognition that the war could not be won militarily against opponents capable of building Dover-sized harbours as throwaway invasion tools. German generals who had conquered most of Europe in 1939 to 1941 discovered that their tactical excellence meant nothing against an alliance that manufactured its own strategic infrastructure faster than it could be destroyed. The contrast between German and Allied approaches to the harbour problem reveals different engineering philosophies and industrial capabilities. Germany spent 2 years fortifying existing ports with 13 million cubic meters of concrete and 1.5 million tons of steel. These massive fortifications represented Germany's only solution to the invasion threat, make capturing ports so costly that the Allies could not sustain an invasion long enough to break out. The Allies built 2 complete harbours using roughly half the material Germany expended on fortifications, made them mobile, and considered them temporary. One harbour was destroyed by weather, yet the invasion continued uninterrupted. This demonstrated the fundamental principle of industrial warfare that Germany never fully grasped. In modern mechanized conflict, the side that can manufacture, transport, and deploy infrastructure faster than the enemy can destroy it holds decisive advantage regardless of tactical outcomes. The Mulberries embodied this principle in concrete and steel. The forgotten heroes of the Mulberry Project extend beyond the immediate construction and operation teams to include the designers who solved unprecedented technical problems under impossible time pressure. Major Alan Beckett, whose floating pier design was selected for the whales, worked in the War Office's Transportation 5 Department, an obscure logistics unit that transformed into the center of the most ambitious engineering project of the invasion. Beckett's design succeeded because he understood that fighting the 23-foot tides was futile. Instead, his roadways moved with the tides, maintaining connection through flexibility rather than rigid resistance. This elegant solution emerged from accepting the constraints rather than attempting to overcome them. Lieutenant Colonel William T. Everall, Beckett's colleague who contributed to the pierhead design, brought experience from railroad engineering to solve the problem of maintaining constant deck height. The spud legs with hydraulic jacks adapted locomotive inspection pit technology to marine applications, creating a system that could support 40-ton Sherman tanks while rising and falling with tidal flow. The civilian engineering firms that undertook Mulberry construction demonstrated remarkable adaptability. Companies like Costain, Balfour Beatty, and Sir Robert McAlpine had built roads, railways, and buildings across the British Empire. Now they poured concrete into forms that would float across the English Channel, welded steel pontoons that must articulate through 40-degree angles while supporting tank traffic, fabricated structures that combined the requirements of ships, bridges, and harbours in single designs. The learning curve was brutal. Early construction encountered problems with concrete cracking under stress, steel warping during welding, and components that did not fit together properly during assembly trials. Each problem was solved through improvisation, testing, and redesign compressed into weeks. The companies accepted financial risk, working under contracts that provided minimal profit margins while requiring absolute reliability. Government inspectors rejected any component that failed to meet specifications, forcing companies to absorb the cost of rebuilding defective units. This quality control, though expensive and time-consuming, ensured the Mulberries functioned as designed. The operational phase of the Mulberries demonstrated that even the most sophisticated engineering depends ultimately on the skill and determination of the people operating the equipment. The Corps of Royal Engineers assigned to Mulberry B worked continuously from June 8 through November 1944, maintaining structures under conditions that varied from summer calm to autumn storms. Repairs required improvisation with available materials, as replacement parts could not be manufactured and shipped from Britain fast enough to address storm damage or normal wear. Engineers learned to shore up damaged sections with timber, steel plate, concrete poured underwater, and whatever materials could be scavenged from wrecked landing craft and damaged vehicles. The maintenance effort involved hundreds of personnel working in cold seawater, often under German artillery fire from batteries that remained active until Allied breakout pushed German forces out of range. This unglamorous work, maintaining floating piers in November, storms off the Normandy coast, received no recognition but proved essential to keeping Mulberry B operational for 8 months instead of the designed 90 days. The American experience at Omaha Beach after Mulberry A's destruction revealed that logistics flexibility mattered more than specific infrastructure. US forces adapted immediately to beach operations, using LSTs, DUKWs, amphibious trucks nicknamed ducks, and conventional landing craft to maintain supply flow. The techniques refined through amphibious operations in the Pacific and Mediterranean theatres proved sufficient when combined with the sheltered water provided by the surviving Gooseberry breakwaters. American logistics officers calculated that beach operations required more vessels and personnel than harbour operations. But the US possessed surplus capacity in both categories. The Navy had more LSTs available than could be efficiently employed through a single artificial harbour anyway. The flexibility to switch operational methods without disrupting supply flow demonstrated that American logistics planning incorporated redundancy and contingency options that proved decisive when primary plans failed. This approach contrasted sharply with German logistics, which depended on specific infrastructure that could not be quickly replaced when destroyed. The legacy of the Mulberry Harbors extends beyond their immediate military application to influence how engineers approach the problem of temporary large-scale infrastructure. The fundamental insight that structures do not need to be permanent to be effective has shaped disaster relief operations, offshore resource exploitation, and military expeditionary logistics. The floating pier concepts developed for the Mulberries evolved into modern modular causeway systems used by the US Navy and other maritime nations. The Phoenix Caisson principle of sinking prefabricated structures to create instant harbours influenced offshore oil platform design and artificial reef construction. The lesson that complex projects can be executed on compressed timelines when necessity demands influence post-war project management methodology. The Mulberry timetable, from Churchill's May 1942 memo to operational harbour in June 1944, proved that 2 years sufficed to solve previously impossible engineering problems when national survival provided motivation. The cost-benefit analysis of the Mulberry project remains subject to historical debate, but the strategic effect appears clearly positive. Total expenditure for both harbours reached approximately £40 million in 1944 pounds, equivalent to roughly £2 billion in modern currency. This substantial investment purchased insurance against the primary risk of the invasion, inability to supply the landing force fast enough to achieve breakout before German reinforcements contained the beachhead. Whether Mulberry A's destruction negated half the investment depends on valuing the psychological impact and the time purchased. Mulberry B clearly justified its cost by landing 4 million tons of supplies before Antwerp opened. Even Mulberry A, which operated for only 10 days before the storm destroyed it, handled approximately 70,000 tons during that period and demonstrated Allied capability to German defenders. The insurance value of having two harbours, rather than relying entirely on beach operations, cannot be calculated precisely, but clearly influenced invasion planning and execution. Eisenhower's endorsement of the project demonstrated that theatre commanders viewed the Mulberries as essential rather than merely helpful. The Mulberry Harbors embodied Winston Churchill's directive that difficulties would argue for themselves. Every engineering challenge proved surmountable when addressed with sufficient determination, talent, and resources. The tidal problem was solved by designing structures that moved with tides rather than resisting them. The wave problem was addressed through multiple layers of breakwaters using different principles to absorb energy. The towing problem was resolved through specialized procedures and accepting slow speeds. The assembly problem was met by prefabricating components sized for available towing capacity and designing connection systems that worked despite imprecise positioning. The maintenance problem was addressed through robust over-engineering and continuous repair efforts. Each solution created new problems that also yielded to engineering analysis. The success of this systematic problem-solving approach under extreme time pressure validated the British engineering establishment's capabilities and demonstrated that innovative solutions emerge most readily when conventional approaches prove inadequate. The human cost of the Mulberry project remains difficult to quantify precisely. Construction accidents killed dozens of workers in Britain. Several tugs and their crews were lost during the channel crossing, some to mines, others to equipment failure or heavy seas. German artillery fire killed an unknown number of Royal Engineers during assembly and operation phases. These casualties rarely appear in invasion statistics, which focus on combat troops rather than logistical support personnel. Yet the engineers and construction workers who died building and operating the Mulberries contributed as directly to victory as soldiers who stormed the beaches. Their sacrifice enabled every subsequent operation, from the breakout at St. Lo through the liberation of Paris to the final advance into Germany. Without the supply flow maintained through Mulberry B and Omaha Beach operations, the invasion would have stalled within weeks, potentially allowing German forces to contain the beachhead until winter ended offensive operations for the year. This counterfactual reality makes clear that the unglamorous work of logistics and engineering proved as decisive as tactical brilliance. The Mulberries represent a watershed in military engineering, demonstrating that industrial powers can create strategic infrastructure as weapons in themselves. The psychological impact on both Allied and German forces exceeded the direct military value. Allied soldiers who saw the harbours gained confidence that their supply lines would be maintained regardless of German resistance. German soldiers who watched the harbours materialise concluded that defeating such an enemy required resources Germany no longer possessed. This psychological dimension of the Mulberries influenced tactical decisions throughout the Normandy campaign. As German commanders recognised that delaying Allied advances mattered little when the Allies could simply manufacture whatever infrastructure or equipment the delays consumed. The hopelessness that pervaded German command after initial invasion week derived partly from watching the Allies build major port facilities from nothing in days, demonstrating an industrial capacity that rendered conventional defensive calculations meaningless. Today, the remnants of Mulberry B rest along the Arromanches beach as monuments to engineering ambition and industrial might. French preservation efforts maintain several Phoenix caissons as historical landmarks. Their concrete weathered by 7 decades of tides, but still massive and imposing. Tourists photograph them without fully comprehending what they represent. The moment when industrial warfare reached maturity, when nations demonstrated they could manufacture complex infrastructure at scale and deploy it across oceans as temporary expedients. The caissons embody the Allied advantage that won the war, the capacity to produce material faster than the enemy could destroy it. German engineers who studied, captured Allied equipment after the war universally expressed amazement at the abundance, the deliberate over-engineering, the assumption that replacement would be immediate if destruction occurred. This mindset, foreign to German industrial practice, shaped by shortages and conservation, made the difference between victory and defeat in extended industrial conflict. The story of the Mulberry Harbors concludes with a recognition that great engineering achievements depend on more than technical brilliance. They require organizational competence to coordinate hundreds of firms and thousands of workers. They demand leadership willing to commit resources to unconventional solutions. They need craftsmen capable of executing unprecedented designs without prototype experience. They depend on operators skilled enough to maintain complex systems under combat conditions. The Mulberrys succeeded because British industrial society could mobilize all these elements simultaneously under compressed timelines. The project demonstrated capabilities that transcended purely military dimensions, revealing the productive capacity and organizational sophistication of a fully mobilized industrial democracy. This demonstration, witnessed by German intelligence officers analyzing photographs of the artificial harbors, contributed as much to Allied victory as tactical success on the beaches. The Mulberrys proved that the Allies had already won the industrial war, making tactical outcomes merely questions of timing rather than ultimate result. The mathematics of the Mulberry Harbors tell the final story. 2 years from concept to operational harbor, 600,000 tons of concrete and steel transported 100 miles across hostile waters, 12,000 tons of supplies handled daily at peak operation. 4 million tons landed through one harbor before permanent ports opened. These numbers represent more than engineering statistics. They quantify the industrial revolution in warfare that determined the outcome of World War II. The side that could build Dover-sized harbors in months and consider them expendable possessed resources that rendered tactical considerations secondary. German commanders who recognized this reality understood that victory had become impossible regardless of battlefield performance. The Mulberrys, those floating concrete fortresses towed across the English Channel in the largest invasion in history, embodied the productive capacity that won the war before the first shot was fired on D-Day. They stand today as monuments not just to engineering achievement, but to the decisive importance of industrial might in modern warfare, forgotten structures that made victory possible through simple genius applied to impossible problems.